Okay, so today we're going to be going over reaction mechanisms and catalysis. So there was a few announcements and a few decisions that need to be made. As for the announcements, it's basically stuff about Chem Olympiad. You can pause and read the announcements here if you wish. Otherwise, just go ahead and ignore them. And then in terms of the decisions, this is mostly just going forward this semester. I'll probably be posting something in Discord to make this decision. So just let me know or just respond in there. Okay, so here is a review question. The above experiment was performed several times and the following data was gathered. What is the rate law for this reaction? And then remember, for the AP chemistry exam, you do not get a calculator, so try to do this without one. So the answer here is actually D. You can solve this without using a calculator, and it's very helpful here for this particular one to change from scientific notation to regular numbers. In this form, it's much easier to see that between reactions 1 and 3, the rate quadruples, and then between 1 and 2, the rate doubles. Since between 1 and 3, the concentration of nitrogen monoxide is changing, then between 1 and 2, the concentration of bromine is changing. You know that the second order for nitrogen monoxide, the reaction is second order for nitrogen monoxide, and first order for bromine. Therefore, the answer here is D, where you have nitrogen monoxide squared and bromine to the power of 1. Okay, so just for review, the general rate law is always going to be determined experimentally, and then reaction orders have no correlation to the stoichiometric coefficients of the overall reaction. We also have some construction going on, so if you hear some banging, just ignore that. So we're going to go and dive right into reaction mechanisms. These are the famed steps to a reaction. A balanced equation for a chemical reaction basically tells you what's present at the beginning and at the end of a reaction. So it's kind of like a net ionic reaction in this case, where the intermediates are eliminated, kind of like how the spectator ions are eliminated in a net ionic reaction. However, many reactions occur in multiple steps that you will not see in the overall reaction. So reaction mechanisms are determined experimentally, and the process is basically guess and check, where a mechanism is proposed as a guess based off of the overall rate that you can find, rate law that you can find, and then they're checked experimentally. The process is actually really interesting. Sometimes you're lucky and you get an intermediate that is itself colored. And in that case, you can use spectrophotometry to find the concentration of the intermediate at a given time. And then sometimes a chemical indicator is used to react with the molecules, but that only works if the indicator reaction is preferential to the rest of the reaction. So then if one of the intermediates is acid-base, pH can also be used. And then there are various other methods that are used to prove reaction mechanisms. The whole process is really interesting. I highly suggest you look further into that if you're interested. So this is an example of what a reaction mechanism will look like. You have like the overall reaction up here, and then you have the steps to the reaction here. They labeled 1, 2, and 3, always done in Roman numerals. Although sometimes in the AP test I have seen it given just as regular numbers. And then each of these reactions is called an elementary reaction, which we'll cover later, more later. And then at the end you're going to have this summation, and then you cancel things that are on both sides of the reaction. For example, the 2C and the B, and then you're left with the overall reaction. In this case, A plus D yields E. And then remember that the chemical equations for the elementary reactions in a multi-step mechanism always add up to give the chemical equation of the overall process. Okay, so there is this concept called molecularity, and molecularity is basically the number of molecules, like individual molecules, in a given reaction. And this ties back to the collision theory, and basically what this is like it's the number of molecules that need to collide with each other with a given energy and a given orientation in order for the reaction to progress. So then you have a couple of terms that go along with it. Unimolecular, which is when only one molecule is involved. Typically, those are going to be decomposition reactions. You have bimolecular, where there are 2 molecules involved. Termolecular, where there are 3 molecules involved. Those are slightly rare. And then you can see, if you think about the collision theory, the more molecules that are involved, the less likely the reaction is to actually occur, because more molecules are needed to collide by chance, and that is obviously much rarer. This is why termolecular and above molecularities are incredibly rare in nature. You almost never see anything with more than 3. The only place that you can ever really see them is in with biological catalysts like proteins. And even then, it's incredibly rare. It's far more likely, even for the biological catalyst, to use unimolecular and bimolecular reactions. Okay, so going into elementary reactions, I mentioned the term earlier. These two definitions are actually the same, but I will differentiate them because they are slightly different. It might be a little confusing if I just give you one of them. So the reactions that occur in a single step, so these would be reactions that essentially don't have a reaction mechanism. In that case, the overall reaction rate is equal to the elementary reactions rate. And then for the second definition, each of the singular steps in a multi-step reaction are called elementary reactions. So in that case, it would be like having, if you go back to the previous slide here, where you have steps 1, 2, and 3, each of those is called an elementary reaction. So 1 is an elementary reaction, 2 is an elementary reaction, 3 is an elementary reaction, and so on. And in that case, with multi-step reactions, the overall reaction rate law is going to be the summation of the elementary reaction rate laws. So for elementary reaction rates, there's a special property, and this does not extend to the overall reaction equation. So for the elementary reaction rates, the reaction order can be determined from the equation. For example, here's one between nitrogen monoxide and ozone, creating nitrogen dioxide and oxygen. Remember that the elementary reactions still have to be determined to be elementary reactions experimentally, but if you're predicting that it's going to be elementary, or if you know that it's elementary, if that information is given to you, you can predict the rate law basically by looking at the molecularity of these reactions. So if you see here, it's going to be one molecule of nitrogen monoxide colliding with 1 molecule of ozone, which is why for nitrogen monoxide it's going to be first order, and then for ozone it's also first order because there's 1 of each. And then the overall rate law is going to be second order because you have 2 molecules that are colliding. In this table down here, there's a summation of basically all the possible types of elementary reactions and their respective rate laws, and then along with their molecularity. This is a pretty good table to sort of memorize. It's not too difficult to do. It's pretty simple, really. But yeah, that's a good thing to know. And then here is a red herring question, type of question from the AP exam. So in this case, it states the decomposition of phosphine occurs via the pathway below. And it gives you this equation. And the question, it's all the way down here. It asks what order is the reaction and why. So in this case, the answer is first order. And if you remember back to when we to the last video or the last lecture, you remember that when you have a table like this, and then half of the reactants or the reactant concentration decreases by half at some given point in time, you know that it has to be a first order reaction. But at the top, it states that it occurs via the pathway below. A valid reading of this question would actually be to assume that the given reaction is elementary, in which case the answer would be rate is equal to K times the concentration of phosphine to the power of 4. But that is not actually the case, and you have to remember that if you're given data, the data is the most important part. And you always go off the data. However, if you are only given the part at the top without the table and without any sort of other graph or other information, in that case, you would actually assume that it's a quarmolecular equation reaction. In that case, you would actually assume that the reaction rate is K times the concentration of phosphine to the power of 4. So when you're determining the rates of multi-step reactions, the relative reaction speeds are going to be given, usually to the right, and you can see that down here, that's kind of what it'll look like. And it's either going to say that it's slow or fast. These are assigned as the mechanisms are proposed, and everything is given relative to the speed of the other reactions. So for example, slow, it could mean a lot of different things, but really it just means that it's slower than the other two steps. And then the slow step is also known as the rate determining step, because that's going to be the most important step in finding the rate law. So you're left with a few possible cases. One where the slow step comes first, one where the slow step is last, and then one where there's a slow step somewhere in the middle if you're given 3 or more steps. And then in those cases also you can have more than one slow reaction. So for the first case where the rate determining step is first, you can see this is an analogy given by the textbook where you have like a bridge, right? And you have one toll plaza and you have another toll plaza. In this case, the first toll plaza, which represents the first step of the reaction, is the slowest reaction. Right, so in that case, it doesn't matter how fast toll plaza B is, right? It's always going to the speed at which cars can pass the bridge is only going to be dependent on toll plaza A, right? And then toll plaza B, I mean, it's faster than A, so it doesn't matter essentially. So in those cases, the rate law of the first reaction is going to be the rate law of the overall reaction. So remember that elementary reaction rate laws are determined from molecularity, and so from the first equation, you can see there's just the A on one side, and so you have rate is equal to K. Yeah, rate is equal to K times the concentration of A. There's nothing else there. And then so the next case is where you have the rate determining step last. And in this case, you can see you have like two fast equations where 1 is fast and 2 is fast. Fast essentially just means that 2 is faster than 1. Otherwise, it would be noted as fast, slow, and then slow instead. So if you have multiple of these stacked, just know that it essentially means that it's faster or slower than the previous reaction. So determined between the so the rate here is going to be determined between the last fast and the last slow reaction. So in this case, it's step 2 and 3. So the rate determining step here would be, well, technically it's going to be number 3, but in order to calculate it, you're going to be using 2 and 3. In this case, you'll notice that the yield signs here are replaced with the equilibrium signs, and the reason here is that all reactions exist in equilibrium, but when you have something like this, where the slowest one is first, and then it progressively gets faster, the products are going to be used up as soon as they're created, right? And so there's not going to ever be like sort of this backlog of reaction products. But in the case where the fast reaction comes before a slow reaction, you are going to have that backlog of products that do not get immediately used up by the next reaction. And if you remember back to chem honors, you know that when you have an increasing concentration of the products, there's going to be a there's going to be a sum going in the reverse direction, which is what you're seeing here with the fast elementary reactions. But then in the case where it's slow and then fast, that is very negligible because it's immediately used up. Okay, so in this case, you're going to look at the rate of the 2 forward and the rate of the reverse. Just as a notation thing, the rate constant K is going to have the subscript 2 or whatever number it is, and then for the reverse, it's going to be negative 2 as the subscript, as you can see here. So the rate of 2 forward, and again, everything is based off of the molecularity. So in this case, you just have B and D, and then for the reverse, it's just C, and that would be essentially just the same as like if you flip the reaction over. And then you have the rate forward is equal to the rate reverse. It's maybe a little bit confusing if you're coming from the equilibrium kinetics, but this equivalence is just assumed for the next step, which is you solve for whatever you have that comes after. In this case, the next reaction uses C, right? So in this case, you're going to solve for a concentration of C. And what you take is you have the two parts, the forward and the reverse reaction, and basically what you're doing is you're just setting them equal to each other, and then solving for the concentration of C here, and then you end up with this where you have the forward reaction constant divided by the reverse reaction constant. That constant divided by constant is still a constant. So in that case, you can actually simplify that. But I'm going to leave off on that for now for one more step. So now you have basically the concentration of C with this in terms of the rest of the rate, and then that is going to allow you to account for basically the products of step 2 that are going back in the reverse direction because you have this backlog because of a slow reaction. And then basically all you do to find the overall rate law from here is to substitute the concentration of C that you just found here in terms of the rest of the rate for the concentration of C in the part 3, which again you're just going to use molecularity, so you have K, that's just a 3 concentration of C squared because you have 2C here. So oops, sorry, 1 too far. Yeah, and so essentially you have this is you're going to substitute in what you just found for the concentration of C based off of the previous reaction. And then you're going to end up with something like this, where you have like 3 different reaction constants, but it's all going to be in terms of B and D, which are the reactants in the previous, like the fast reaction. Yeah, and then essentially these are all just constraints, so we can reduce to a new rate constant K. Yeah, so the overall reaction here will just be rate is equal to K times the concentration of B squared times the concentration of D squared, and that's pretty much it. So this is going to be the case when there is a step that is slow, that's somewhere in the middle. So in this case, you have like a few different types that I put up here. Basically, all you need to know is that they sort of stack on top of each other. So for example, for number 1 here, when you have 1 and 2, like 1 is fast, 2 is slow, and 3 is fast. You can see if you look between 2 and 3, you're gonna have the same case as case 1, where it's the fast step is last, right? So it's all gonna be determined by number 2, but the rate of number 2 is determined by the rate of number 1 as well, because that one is fast. And sorry, that there should be an equilibrium sign in there. But essentially, you're just gonna be doing the rate determining step as last between 1 and 2, and that's all you need to worry about. And then for the third case, for the second case, where you have where the first reaction is slow, second is fast, and the third is slow. In this case, it's basically going to be as if number 2 doesn't really exist. Essentially, the rate of the first one is going to determine the rate of number 2, and then from there you can combine them the way shown in the previous rate determining step as last here between 1 and 3. And then if you have a fast, slow reaction, essentially you have to do it twice, where you have first you determine between 1 and 2, and then between 2 and 3. But the assumption is essentially that these just kind of stack on top of each other. You can use the previous 2, where either you have rate determining step as first or rate determining step as last, in between these different elementary reactions. So here's a sample multiple choice question with a multi-step reaction that takes place in the following elementary steps, and then you're given that. And then you're asked to find the overall balanced equation for the reaction, which is just going to be basically crossing out things that are shown on both sides. And then for number 3, if step 2 is slow, which means everything else is fast, what is the overall rate law? So I encourage you to pause and try to figure that out here. So the answer here is, for the first one is D, and I'm pretty sure you guys can figure out why. And then for number 3, it's A. I won't go through this, but if you need help with that, go ahead and message me on Discord, and I can send you the work. And here is a sample FRQ with the following results obtained from an experimental. And this, I'm not actually going to have you guys go over this, but basically what you're seeing here is with part D, where the following reaction mechanism is consistent with the rate law established in A. So if you remember back to our first lecture, you're going to be finding the rate law just like that. And then in part D, what you're finding is you're going to be finding the rate law based off of these 2 different mechanisms, and then finding which one matches up to A. And that's all there is to it. Very occasionally, you will see on the AP exam where they ask you, like, where they give you some data, and then they have you write the rate law for the reaction, and they ask you just to like open-endedly write a reaction mechanism. You really only see that on the really old exams. They tend to not do that anymore because there's literally infinite possibilities for the reaction mechanisms, so it's really difficult to grade for them. So they don't tend to do that anymore. However, I do remember seeing them in one of Mr. Riva's exams, so you might want to get at least a little bit comfortable, try it out a few times, so that you know how to do it like that. But it's pretty easy. You just have to like trial and error, and then just find one where once you calculate it out, you end up with a rate law that's the same as the rate law given in part A or whatever part you calculated the rate law in. So now we're going to be moving into catalysis, which is when a catalyst is used to speed up a reaction. Catalysts are never destroyed or consumed, and there are a couple of different types. You have homogeneous and heterogeneous catalysts, and basically that's given by the same or different state as the reactants. And then you have inorganic and organic catalysts. Inorganic catalysts tend to be noble metals, for example, platinum, gold, silver. Usually you don't see gold just because it's expensive and doesn't actually do a lot. But platinum is very common. Palladium is another one that's very common. Silver is very common. And then the AP chemistry and most of Chem Olympiad only deals with inorganic catalysts. I've seen like one question ever on organic catalysts, so it's probably not too big of a deal. And that was on Chem Olympiad, that was not on AP chemistry. For solids, do note that the catalyst efficiency depends on the exposed surface area, just like it is for reactants. So for a common question on the Chem Olympiad would be, you have like two different catalysts that are the same element, but one's as like a solid brick, and the other one is as a fine powder, right? In that case, the fine powder is going to be much more efficient than the solid brick of it, and that's just because there's more places for the elements to react on. And then essentially, there is one special kind of catalyst called palladium on carbon. That one's just, it's just kind of interesting to look at. What it is it's palladium, which is a metal, dispersed onto carbon, and it's used a lot in organic labs. And I've seen it a couple of times, numerous times on the Chem Olympiad exam, because it's a very good example, like a very common example of a catalyst that's used as, that's far more efficient than just say like powdered palladium, because of the greater surface area that's achieved by putting it, finally dispersing it over these little balls of carbon. So catalysts work by creating a new reaction mechanism where the steps of the reaction have a lower overall reaction activation energy than the original reaction. So here you can see like a graph of it, and so here in blue you have the catalyzed reaction where you have 2 steps, but both of those have a lower activation energy than the overall reaction up here, which is why they speed up reactions. Biological catalysts tend to work in essentially the same way. They actually also eliminate the orientation factor, unlike inorganic catalysts. But you do still consider, so catalysts when they create a new reaction mechanism, essentially what they're doing is they're reacting with the reactants of the reaction to basically create a new intermediate molecule. And the same thing is kind of done by biological catalysts, but it's actually not held together by real bonds. It's held together by intermolecular forces, which is really interesting. But in the sense where you're just kind of thinking about it, you will consider it as like almost as if it is a new molecule, even though it's technically not bound together. So a very common thing that you're asked to do in both AP Chemistry and Chem Olympiad is differentiate between catalysts and intermediates. Intermediates are species created and consumed during the course of a reaction in a reaction mechanism, and the catalysts are present at the beginning of the reaction, form an intermediate, and then they're reformed at the end of the reaction. So you can see here basically what that'll look like. So for intermediates, you just like the 2C here, that's an intermediate, and it's just consumed during the reaction, you never see it again. For catalysts, they're actually on the outer parts of the reaction, where you have you have the catalyst at the beginning and you have the catalyst at the end, and that's very important because again, catalysts are never consumed or destroyed in a reaction. So there are two basic question types. Type 1 is graph labeling, where you have to label reactants, products, catalysts, intermediates, and then the activation energy and delta H. You're going to have like basically a blank version of this graph here, and then you would have like you would write in your reactants here, the products here, and then the catalyzed reaction, you would specify that it's the one with the lower one here, and then the intermediate is here on the catalyzed version, but it's actually here on the uncatalyzed reaction. There is like a thing in between here, which is also, I guess, technically an intermediate, but you wouldn't really consider it so because the true intermediate is going to be in between. And then the second question type is determining intermediates versus catalysts based on the proposed mechanism. And here is a sample of that type, which is number 2 down here. This is the same multiple choice question as before, but it states what is the function of species B in the reaction. You can see B is present at the very beginning and at the very end, so you know that it's a catalyst because it wasn't consumed throughout the course of the reaction. And the answer is, the correct answer is D. It lowers the overall activation energy of the reaction, which is how all catalysts work. The C is kind of there as like a red herring. It is a catalyst that changes the overall order of the reaction. Catalyst will not change the overall order of the reaction. So that answer is wrong. That's pretty much it for this lecture. Next meeting/lecture, whenever that is, we will be starting the new topic of equilibrium kinetics. Make sure you check out the announcements at the beginning of the video and answer the survey in response to sort of what we're going to do going forward this semester. Other than that, thanks for watching/listening. Have a nice day.